Okay, welcome. This will be a lecture on delays in digital circuits. So in the upper left corner, I showed a basic simple logic circuit, a NAND gate followed by an OR gate. And then on the right, I showed kind of a CMOS picture of that, the FET diagram of the same circuit, and then a timing diagram. And I'm going to use these pictures to illustrate what's going on here. So I want to illustrate node 1, the node between the NAND gate and the OR gate. So I showed it in the logic circuit on the left, and also in the CMOS circuit on the right there, I showed all of the conductors that are connected to node 1, including the transistor connected to input A. And then in the timing diagram, you can see that when A goes high, when B is already high, we're going to drive the node N1 low. And since the input C has been low the whole time, the output Y goes low. So take a moment and make sure that you agree with my timing diagram there. So focusing a bit more on that node N1, on the right there you can see in the FET diagram, I added a single capacitor. So I'm going to look at all of that, all those conductors highlighted in blue as collected into one single capacitance. And that's a fair thing to do for a basic analysis because all of those conductive elements are connected and they're all separate from ground. And so there will be capacitance between all of that highlighted node and ground. And in fact, you might have the idea that if I had other connections to node 1, let's say node 1 also drove another OR gate and another NAND gate and maybe an inverter, that I'd add more and more conductive material to N1. And if I drew the whole circuit diagram, you'd see more structures connected to N1, and that capacitor would get bigger and bigger and bigger. So the more things that are connected into a given node in a CMOS circuit, the larger the capacitance is. Okay, back to the timing diagram. That shows the kind of timing diagram we've been looking at in the class so far. It's a logical timing diagram just indicating the logic of the circuit. You know, when A and B are both high, node 1's low and therefore the output's low, again because C's low the whole time. But what's really happening on the right there, I've added a resistor. When we turn on the FET connected to A because A went high, now I'm going to drain current from node 1 through that resistor down to ground. And we talked about it briefly earlier in the class. Anytime I'm moving charge from a capacitor through a resistor, well, that's going to take time. And you can calculate the amount of time based on the size of the capacitor and the size of the resistor. Now, for this discussion, I'm not too worried about quantifying numbers and coming up with actual times. Just want you to note that it's not zero time. It's going to take some time to empty that capacitor down to 0 volts or near 0 volts so that in turn the output N1 and Y can also be driven down to 0 volts. And again, the larger the capacitor, the more time that'll take. The larger the resistor, the more time that'll take. Oh, there's a little red arrow showing current going from the capacitor through the resistor down to ground. So I kind of blew up the timing diagram here in the middle bottom there. And again, that's the kind of timing diagram we've been using so far, but really it should look more like this. It should show that it's not an abrupt edge that happens all at once, but there's some time involved. So I modified the node 1, and that would be a voltage representation of node 1. I modified it to show a slower transition that happens over some amount of time. And that's a more realistic picture, what happens. And then I went ahead and modified the other traces as well. It's likely that the inputs A and B and the output Y are similarly driven by circuit nodes that can't transition all at once. In fact, really, no circuit node can transition all at once. Signals transport charge, voltage, and that takes time. It's always going to take time to move charge onto or off of circuit nodes, and so timing diagrams, if they were a little more accurate, would show this gradual rise and gradual fall time instead of all at once. Well, here I indicated the 50% voltage level on the node A that's responsible for causing node N1 and node Y to go low. And then I showed another line at the 50% voltage on node 1. And now you can kind of see the time. The time between A going from 0 to 50% amplitude, and in response, the time it takes N1 to reduce to 50% amplitude is shown as a measurable amount of time. And I'll just for now call that delta T. And that's a more realistic indication of the delay. And so whenever you see a combinational logic circuit, its outputs are going to be driving other inputs, and those signals that it's driving, those inputs to other gates, are always going to have some amount of capacitance, and we're always going to have to transfer charge from that intra-gate node to VDD or ground, and that's always going to take time. So looking back up at the circuit on the left there, the NAND gate, I could say that based on this timing diagram picture, that the delay through the NAND gate is delta T. What I mean by that is if I change A or B, and as a result the output N1 has to change state, that there's going to be time delta T transpiring before the input change is reflected in the output. Okay, let's look at this a bit more closely. There's the circuit again and the timing diagram, but now I'm going to introduce this delta T time. And you can see I allowed delta T time to pass after A transitioned. So in the previous timing diagram, at that second red line, that's when the node N1 transitioned. I'm not showing that now, but I am showing that then Y transitioned another delta T after node 1 transitioned. And the idea being that every logic gate in the circuit is going to introduce some amount of delay. Okay, so quick review. Electronic signals use charge, and to move information, we've got to move the charge around a circuit. And there's matter there. It takes time to move charge, so logic circuits are always going to exhibit some amount of delay. Now, delay limits the execution speed of a circuit, and so that limits the bandwidth of a circuit. We haven't talked much about that yet in this class. We will talk more about it going forward, but you could imagine that as we create more complex and more involved digital systems, that one operating parameter that people pay attention to is how quickly we can move information through the circuit. You probably witnessed over time that computers they did for a while, get faster and faster and faster. And that's because we got better and better at moving information through combinational circuits more quickly. So if we want to minimize the amount of delay, we can do certain things. We can make the transistors have less resistance when they're on. We can make smaller circuits so there's less capacitance to drive. And that's about it really. We can come up with ways to just move current more quickly around the internal nodes of a circuit. Now, we looked at in the previous couple of slides the fact that moving information through logic circuits causes some delay. In other words, there's some amount of time between when an input changes state and when the output will change state. And that's an issue we're just aware of and we deal with, and we try to make that delay be smaller and smaller. But there's another issue, and that's what I want to focus on now. So in the picture here, when signals pass through combinational logic circuits, they can bifurcate or fork and then recombine. And that's what I'm showing with the signal B. Signal B goes through two different pathways. to affect the output Y. One pathway has an inverter and the other one doesn't. And so it makes sense, based on our previous discussion, that the pathway through the inverter is going to encounter more delay than the pathway that doesn't go through the inverter. And that's what I want to look at to see if that can create an issue. So here's just a representation of the circuit and its logic equation and its K-map and a timing diagram. And so far, this is all that we've seen before. The timing diagram shows that if B changes, well, first of all, I set A and C high and left them high so that they don't affect the outcome Y. A and C both go to AND gates, so by making A high and C high for the entire duration of this small simulation, those signals don't affect the output. In fact, there's a term for that. We're saying we're sensitizing the output Y to changes on B. And we sensitize the circuit by, again, driving A and C so that they can't affect the outcome. And then I let B go from low to high to back to low. And if we just looked at this as straight up logic without worrying about time, then the output would always be high. In fact, you can see that here, that in the left part of the diagram, the output Y is high because A is high and B is low. That's the first term in the equation, or the leftmost loop in the K-map. And then in the middle of the timing diagram, the output is high because B and C are both a 1. And then again on the far right of the timing diagram, the output's high because A is a 1 and B is a 0. And so again, the green loops would be the left loop, sorry, the green areas in the timing diagram would be the left loop in the K-map. And the purple area would result from the term B and C, and that's the vertical loop in the K-map. Okay, so that's without any time included. Now, if we add some time, and in the upper left diagram there, I'm showing that the inverter now, I'm going to add an arbitrary amount of time called delta T inverter. And then for all three logic gates, I'm going to add another amount of time I'm calling delta T gate. And those times don't have to be the same. In fact, they wouldn't be the same in a real circuit because there'd be different amounts of capacitance on the output, and the transistors might be slightly different or further apart from each other. So those numbers could be independent and could be anything. It doesn't really change the discussion. So I'm just going to choose a random kind of time, and I'm showing it in the timing diagram there. Some amount of time for information to pass through the inverter, and then some amount of time for information to pass through the logic gates. Now I've also named three of the internal nodes. Node 1 between the inverter and the upper AND gate, and then nodes 2 and 3 are the nodes between the AND gates and the OR gate. And then I'm going to step through the timing diagram by adding those nodes to the timing diagram. So now I've added node 2. Well, node 1, first of all, was just the output of the inverter. So node 1 is just the inverse of B, but now each transition on the output of the inverter on node 1 is only happening after time delta T inverter. So I'm showing that delay time through the inverter. And then node 2 is the AND of node 1 and A. And now I'm showing node 2 with a smaller delay time, in this case delta T gate. I'm showing node 2 transitioning after that delay time as the ANDing of A and node 1. And then I'm going to add node 3 in, and node 3 is the AND of B and C, also after time delta T gate. And so you can see there that node 3 transitions high, delta T gate after node B transitions high. So okay, so far not too complex, just showing just delay going through logic gates. You might want to pause and make sure that that makes sense to you though. Now when I add Y in here, here's where it gets interesting. Y is the ORing of node 2 and node 3. So look at node 2 and node 3, and you can see there when B goes from high to low, when B goes from high to low, there's a brief amount of time when node 2 is low and node 3 is low. And therefore, the output OR gate that's driving Y is going to have to show a transitory time when the output goes low, because both of its inputs, node 2 and node 3, they're both low. So I'm showing then that this low period is going to be the same amount of time. It's going to equal a time, same time as the delay through the inverter. And I'm also showing that the OR gate has a little bit of delay, and I'm showing that as a delta T gate. So the negative excursion on the signal Y, the downgoing excursion on the signal Y, happens delta T gate after node, where are we at here? After node 2, after node 3, sorry, goes low, and then it lasts for delta T inverter. Now, that negative excursion wasn't planned. We didn't want it to be there. It's not part of the function of the circuit we had imagined, but it is there, and it's there because of the inverter. The inverter added some delay to one leg of the circuit, but not the other. And that delay showed up then in the timing diagrams you can see for node 1, node 2, and node 3. And when those nodes are combined to drive Y, the output is an unwanted, maybe unexpected, short-term negative excursion on the output Y. And again, the duration of that short-term excursion is going to match the delay time through the inverter. So that's going to be a very small amount of time, but it's a non-zero amount of time. The question is that an issue? Well, yes and no. So that unwanted negative excursion on Y, in this case, is called a glitch. Glitches are caused by differential delays through legs of a circuit. And there's really nothing we can do about them. When we do simulations with actual time included, it will turn out that if a signal goes through more than one path through a circuit and then recombines at the output, and those paths have different delays, glitches will result. Really can't do much about them. So the assumption is, or the rule is, that anytime any input to any combinational logic circuit changes state, you should assume the outputs will have glitches. So here I'm showing a 5-input, 3-output circuit. And if I changed A, B, or D, or C, or any input, I should assume that X, Y, and Z may all have glitches on them, unless I prove otherwise. And that's kind of a key takeaway, that combinational logic circuits, the outputs from combinational logic circuits can and will glitch anytime any input changes. You should assume that, unless you prove, by analyzing the circuit, unless you prove that no glitch is possible. So in general, as you're designing combinational logic circuits, and we'll come back to this a couple of weeks later, you should assume that combinational logic outputs glitch anytime any inputs change. Now, if we dive a little deeper here, glitches can only form in response to what's known as a hazard, or a hazardous transition. So notice the equation on the left and the K-map on the right. In the equation on the left, you can see that the term B is inverted in one term and not inverted in the other. That's called a hazard, or a hazardous transition. When you see that, that's your clue that if B changes state, because it's coupled in both terms, if B changes state, that Y could have a glitch. You'll notice in the K-map, there's two separate loops. And if we go from the case where, say, A and B bar, the loop on the left, is driving the output low, to the term, high, to the term where B and C are driving the output high, we've got to go from one loop to the other. And that's also a visual clue that there's a hazardous transition. Anytime you're going, in a K-map view, from one loop driving the output high to another loop, when you leave one loop and enter another, that's also the hallmark of a hazardous transition. So typically, we're just kind of aware that combinational logic circuit outputs glitch. We're just aware of it, and we don't really do a lot to try to take them away or to eliminate them. In rare cases, you might need to eliminate a glitch. And that typically would be if you're designing kind of sensitive circuits, memory circuits, which we haven't talked about yet, but we will later. If you do come across a situation where you really need to remove a glitch, you can do it, but you have to add redundant logic. The first thing you do is identify all the coupled terms. So here's our example circuit again, and the logic equation and the K-map, and I'm showing how you can identify the coupled term. You'd look for an input variable, a signal, that's inverted in one term, but not inverted in another term, when those two terms then can recombine to drive the output Y. So you can see it as a coupled term in the logic equation, or you can see it as loops in a K-map with no joining loop. Then we want to identify redundant logic that we can add to the circuit for each hazard. And you can do this either in the logic equation view or in the K-map view. In the logic equation view, I've taken the term A and B bar, or B and C, and factored out, I guess, mentally, or I could do it on paper, I could remove the coupled term, which is B bar and B. And then the leftover signals, A and C, kind of form the residue once I remove the coupled term. I can AND those two together to form a new term. Or in the K-map, I can add a redundant loop. Doesn't change the logic, but it does add an extra logic gate. And those are the redundant logic gates that I can add. And if I do that and add them back into the circuit, there's no chance of forming a glitch. Why? Well, if you recall at the outset in the timing diagram, I said that we're going to leave A and C both high to sensitize the output Y to a change in B. So I know the signal A and C are both high. If I combine those into an AND gate, I know the output of that AND gate is always high, and it's driving the OR gate. So I haven't changed the overall logic of the circuit. I can see that from the K-map, but I have added a term, a redundant extra term, that removes the chance of a glitch happening. And so that's the trade-off. I can add extra logic that does not affect the outcome or the logical outcome of the circuit. I can add extra gates that only serve to remove possible glitches, but they don't change the output logic. Now, let's see. Okay, last slide here. The same issues and the same remedies exist for POS circuits as well, and you get to explore those in this week's project. So before I let you go, a couple of things. First of all, the next small lecture I posted, it's like 10 minutes, just goes through a more elaborated example of removing possible glitches in slightly larger circuits, and there's also a POS example in there. But just want to reiterate that really the takeaway is that for combinational logic circuits, for any combinational logic circuit that you design part of the project in this class or going forward in your design life, anytime an input to a combinational logic circuit changes state, you should suspect that immediately after the input changes state, one or two or all the outputs, however many outputs there are, you should suspect that they might have a glitch unless you prove otherwise. And then if you really need to remove the possibility of a glitch from an output, you can do that by adding unnecessary redundant logic gates to the circuit. So you're making the circuit less efficient by adding extra resources, but in doing so, you can remove the possibility of a glitch forming. Again, that's a fairly rare thing to have to do, but it can be done. Okay, go watch the next video, and then I will see you back in class.